Okay, so welcome everyone. So I'm Randy, and I'll be co-presenting this reading group session with Sophia. Today we'll be presenting on the paper entitled MAST, a memory-augmented self-supervised tracker. So this paper was authored by Zihang Lai, Erica Liu, and Weedy Z from the Visual Geometry Group at the University of Oxford. This is a broad overview of our presentation, so we'll be defining some key terms, given some example applications of video tracking. We'll then move on to cover some of the prior approaches and the categorizations within this field. Within this area, we'll sort of give a broad overview of some of the disadvantages kind of experienced by these models. Following which, we'll introduce the method proposed in this paper. We'll discuss some of the specifics associated with the model. And then we'll close up by mentioning the results as well as the conclusions and the key findings of this work. So what is tracking in videos? So tracking is the process by which moving objects are followed dynamically across video frames. So we decided to give two key application videos over here as examples. So on the right, we have a case where pedestrians are followed in a crowded scene. So this has some surveillance value from a security standpoint. So for example, maybe one of these pedestrians is guilty of shoplifting or something like that. This information could be given to law enforcement, which will identify, what time it happened, the possible event happened, as well as the direction in which the pedestrian was headed. So there's some real value there in that segmentation example. The example on the left is an example of human-computer interaction. Essentially, in human-computer interaction, what happens is that the way in which this hand is moved conveys a particular signal or a message. So video tracking would assist you, in essence, in trying to figure out what that message is. So that's a really other nice example of video tracking. We could categorize video tracking into three main categories. So there are supervised models, semi-supervised models, and self-supervised models. In a supervised model, what you essentially have is you have all of the masks available to you beforehand for training. So you have input images, output masks for sort of like a unit architecture, perhaps, if you want to think about it like that. And all of this is provided beforehand. In semi-supervised training, essentially what you get is you get less labels. So you might have one fully labeled frame, and you have to sort of determine what the other labels are based on this frame. So there are some key disadvantages to all of these approaches, and I'll just give some brief coverage of it. In supervised models, it's a very memory intensive process because these frames need to be stored on disk, and then they need to be brought into RAM at training time. So there is a disadvantage there. In addition, for supervised models, there's an associated time consuming workflow for your manual annotation process. Essentially, all of these frames need to be human annotated, and it's a very challenging and time-consuming work. For semi-supervised and self-supervised models, it's computationally intensive because you do need to determine what the next mask or label is on a frame-by-frame basis. And it gets to be a bit challenging from the computational side. So it does sort of solve these problems, but it sort of introduces this problem. So that's the honest coverage of it. We did a sort of categorization of the main tracking algorithms, and we sort of put it into segments. So in visual object tracking, this is where you use bounding boxes. In semi-VOS, you're using pixel level segmentation masks. And subcategories of this include segmentation-based and propagation-based models. So I'll give some explanations of these two types of categories afterwards, right here. In a segmentation-based model, what you essentially have is a segmentation model in the middle. So you could think about this as perhaps like a unit or something like that, right? And it takes your image as input and it gives you your mask as output. The only problem with segmentation-based tracking in this sense is that if you take a pre-trained model, it might have been trained on 1,000 or 1,500 classes beforehand, right? And maybe your video data set only has 10 classes. So what do you do in that case? Well, what is typically done in that case is that it just chops off the last layer of the network. You'd add 10 activations and you fine tune on the first mask itself. So in essence, now what happens from the second frame, third frame, fourth frame is that you're fine tuned, your pre-trained segmentation model is fine tuned on your first mask, and then it's applied for your further masks. right? So that's segmentation-based tracking. For propagation-based tracking, it's a bit different. So essentially what you get is you get one fully annotated frame, which is your frame 1, and then you have some models in the middle here that propagate your frames as you move forward. So it's called propagation-based. So based on our research, the typical way in which this is done, this blue box is implemented. It's done using something called optical flow. And essentially optical flow is a computer vision algorithm that looks at tracking moving pixels across video frames, right? Successive images, if we could think about it like that. But what is needed here is that we need to have some concept of memory. You need some concept of memory because you have some pixel level mask here and you want to propagate it in a meaningful sense. So what happens is that a lot of these algorithms include, at least the traditional algorithms included GRUs and LSTMs. So much like a sequence model for language translation would have included. What has been happening recently though is a lot of these models include attention mechanisms because attention mechanisms work much better than RNNs anyway. So they have been finding great use in this sort of video annotation and tracking field. One of the things we wanted to cover as well is that this paper, they employed a lot of tricks to try to kind of get the accuracies to kind of improve. One of these tricks is that they converted their RGB color space into a new color space called Lab. And just to give a sort of bird's eye view appreciation of this, when you have an RGB color image, what typically happens is that if you were to plot them, if you were to plot the individual inter-channel graphs, you see there's a high level of correlation between channels. And why this is dangerous or less useful for us in a classification standpoint is that you could think about these RGB channels as feature vectors, F1, F2, and F3. And if your feature vectors are heavily correlated, then it doesn't actually give you any complementary information for classification. So in Lab, what they do is they do a non-linear projection to a new color space. And based on these scatter plots, at least, it shows less of a correlation. So we actually have more complementary information for classification here. So this was a key design choice made in the paper. And I think based on the plots, it was a judicious and well-justified design choice. I'll be given a broad overview of the attention mechanism before I hand over to Sophia. Essentially what this attention mechanism does is this first formula here, it generates its pixel level reconstruction for frame T. And how it works is that, so it uses a triplet Q, K, and V, so query, key, and value for attention mechanism. V corresponds to previous frames. AI corresponds to the feature similarity for pixel J in the T-1 frame compared to pixel I in the T frame. And the A matrix, which is the affinity matrix, it comes from the softmax implementation here. Q and K, query and key, interesting vectors. You'll be hearing more about them later on in the presentation. Another thing I want to talk about, which I think was a really good choice, was the use of photometric Huber loss. So typically what happens in this sort of regression model, and it is a regression model because we're trying to generate one mask from another mask, and it's an array of numbers. So it's more of a regression problem than a classification problem. It's better framed that way. Huber loss is a bit interesting because what it does is that when the pixel values are far apart, it doesn't penalize it with a large loss in the sense that squared error would. Instead, what it does, it sort of caps the loss. It applies a ceiling to it. So ZI, so IT and I hat T corresponds to pixel values normalized on a scale between -1 and -2. And what would happen in this case is that for the maximum loss you would have is 1.5. So you just a difference of 2 here minus 0.5. In a squared error sense, that loss would have been 4. So it definitely pays less attention to outliers, and that's the value of this for this sort of image regression model. And with that, I'll pass it over to Sophia to explain the memory tracking algorithm.
Thank you. Okay, I can share now.
Yeah.
Thank you, Randy. So more on query key and value. We'll learn here the method they're using. It's a multi-frame tracker, or in a sense, the way that they're propagating the mask and using information from previous frames, which is, yeah, essentially it's in a dancing visual tracking. Models treat keyframes as memory, which are shown as K here. And then it uses attention mechanism that has been mentioned to retrieve candidate frames for pixel reconstruction. So Q and K are shared weight feature representation that have been computed after passing target frame, which was our I of T, to Siamese convolutional network. Siamese network, they've used ResNet 18 architecture. And technically the encoder here, as you see in the picture, is essentially the Siamese ResNet encoder. More about V here, value. In training, we have value as the frame itself, but in an inference level or testing level, this becomes as our mask. Okay. One thing that they also did, they extract region of interest, or ROIs. Because of reconstruction of high resolution images are memory intensive, they come up with this solution to have ROIs. And we go further about the ROIs, but just remember the ROIs are essentially the keys that they've been used before. So here in the query frame, query pixels are being processed to determine similar regions, and using that, H or our heat map is created where it has collected the affinity score. And so this is our H, and technically this is our affinity score, which uses softmax. And it uses in a way that both query and our key, both for short-term and long-term memory has been used. So N presents the number of previous frame. So here we have a softmax of Q and K in a sense. That would create our heat map, which would be technically, which has contain affinity scores. Then with using a window C or the center coordinate, we would have a window C that approximate or estimate the center location of the region. So how it does it, it uses, this is our center, or let's say our window. Using our affinity score, it would extract, per se, important information and extract this correct region on this heat map. After this, it uses bilinear sampler for resampling our ROI, or in other words, our keys. Implementation, the way they've done it, so they created a ResNet architecture. The encoder is based on ResNet 18. And they didn't use any weight, so it's just the architecture, and they randomly initialize the weights. This training is then done in 2 steps. First was pre-training, and then would be fine-tuning of that training on that trained model. In pre-training, batches of 24 of 2 frames are inputted in the network, which one of them is reference frame and the other one is target frame. Adam optimization has been used. Also, they've done about 1 million iterations on that. The way they chose their learning rates is based, it's based on a decay-based learning rate scheduler. And for fine-tuning, that is where memory-augmented model comes into play. And the input then would be multiple reference frames with the target frame. Also, fine-tuning was done on a lower learning rate as before. On an inference side of it, trained feature encoder, it contained affinity matrix of target frame versus the reference frame. And this affinity matrix is then creates this mask based on propagating frames. So it's a frame by frame basis again. Oh, and it's important to mention, well, of course, it's in a dynamic way. So one other thing that was really great in this paper, and it was really different. It was the way that they had their matrix for evaluating the unseen versus seen category. And using this, they show how it's actually well generalized on these unseen categories. Also, of course, seen category performance outperforms the unseen ones. But they also did it in a way that if unseen categories performance is higher, then it gets rewarded. There was another thing to mention that helped the model with accuracy. It was image feature alignment. So when using bilinear sampling, as I mentioned before, it caused a lot of misalignments. As you can see in this picture. So here's the CNN kernel center, but then the bilinear sample happened here. So they kind of did a customized sampler and they tuned it in a way that the center would actually fall into the CNN kernel center. Yeah, that helps with accuracy around about more than 2%. This is the result, the comparison results from self-supervised. The first three are self-supervised versus supervised method. And these methods are all been on a video segmentation result with YouTube VOS dataset, which has been their benchmark. They got a very good result on a second, they received a second score comparing to all of these, comparing to the supervised. And in self-supervised, they are actually leading. And also for generalizability gap, that's what we talked about unseen versus seen. This shows actually the lower the value is, the more it has been generalized. And the average over here is about 11, and they reached 0.4. So in conclusion, the model was very accurate and generalized well on a pixel level tracking. And they didn't do, so it was a self-supervised. So there was no semantic annotation. There was no need for annotation whatsoever. Also, the unseen objects performed very well, which actually here they come and say like it's a stronger competitor. It's a very strong competitor comparing to supervised, because supervised actually uses many annotations and it's very memory intensive. In this way, they're not only they did a better job on a self-supervised previous methods, but also it's very competitive with the supervised. That's about it for us. Thank you. If anyone has any questions, please ask us.
Do you have any examples of what the images look like when you apply that, the different color scheme? Was it LAB or LBA? I forget what it was called.
It's a lab color scheme.
Yeah.
Yeah.
I believe there might have been something in the paper. Do you have anything?
I didn't see, no, there was nothing in the paper per se to show the image, but it was just that the figure that they show the correlation of pixels. And lab is, so lab color space is L is for brightness. So that's the main thing, that the brightness is separated from A and B. Not, yeah, it is separated. And A and B, A has, I believe, do you remember, Randy, was it yellow and?
Yeah, essentially A and B were like combinations of colors. But one thing to note though, Marco, is that RGB color images, they have meaning to us visually, right? It's just because they correlate so heavily that this paper used lab. But if you look at a lab image, it doesn't actually make sense to you visually. It just really does this decorrelation, which is useful from a classification standpoint.
Okay, so I see. So would the image actually look different from the original image, not just have different colors?
It would look different. Yeah, it
Yeah,
would look differently. Yeah.
they would look
Okay.
different. Yeah, because
Gotcha.
it would be essentially on a different color space than RGBs.
Gotcha. Okay. Thank you.
Yeah, no problem.
Okay.
Any other questions, maybe?
Or clarifications, anything. And by the way, we actually took a look at their GitHub. It was posted to be released, but it hasn't been released. So it was a good work and very well done research on their end. But we couldn't find any codes to be able to implement it.
Yeah, we would have really honestly liked to, but I guess they just didn't release it as yet. Hopefully they release it soon though, because I would like to experiment with this method.
Yeah, I think they've used MATLAB. Maybe there's a part that they want to do it by Python. Yeah.
Any other questions, maybe? I guess we have a quiet audience this time.
We have a quiet audience. Yeah. All right.
Okay.
Hopefully you guys enjoyed it.
Yeah. And I guess you could always just